5 electrons in nitrogen. Hydrogen, we have 3 hydrogens. Each hydrogen is 1 valence electron. So altogether we have 8 electrons total. And then we try to come up with a symmetric structure. You can't put the least electronegative in the center here for this because the least electronegative would be hydrogen. The problem with hydrogen is hydrogen only wants to form one bond, like chlorine. You know, here, hydrogen just has 1 valence electron. So we'll stick nitrogen in the center and then bond 3 hydrogens to it. Hydrogen only needs a duet. And so we'll just complete the octet on nitrogen. So this takes care of 2, 4, 6, 8 electrons. You can see it has an octet here. Now, the octet is one way of counting electrons. We have 3 ways of counting electrons in the exact same structure. The 3 ways to count electrons. The first way is the octet, slash duet. This is the number of electrons surrounding the atom. And so, in terms of this is how we count it in the structure here. Surrounding hydrogen is just 2. So that's a duet, that's a duet, that's a duet. Hydrogen is in the first row, so the first energy level, so it only takes 2 electrons to complete its shell, first shell. Nitrogen, we double count here. Nitrogen has a total of 2, 4, 6, 8 electrons surrounding it. And so nitrogen has an octet. Hydrogens have a duet. The next way we count electrons in a structure is by oxidation state. Oxidation state, we assume that all bonds are 100% ionic. We have different you remember polarity, we have different polarities for the bonds, from non-polar to polar covalent to ionic. And so it doesn't matter, we would classify, what would the nitrogen-hydrogen bond be? Would that be non-polar? Would that be polar covalent? Or would that be ionic? And so we would need the electronegativities to figure that out. And so let's take a look at the electronegativity chart again. Let's see what we would classify it as. And so if we look at nitrogen, nitrogen is more electronegative than hydrogen. Nitrogen's at a 3.0, hydrogen's at a 2.2. So 3.0 minus 2.2, that tells me that the bond in this, we call it delta En. Delta En is the difference in electronegativity. Nitrogen, 3.0 minus hydrogen, which is a 2.2, gives us a delta En of 0.8. 0.8 is approximately what type of bond is that? How would we'd call it a polar covalent bond. And so really the bond is polar covalent, but when we count the electrons, this is like a bookkeeping method. Oxidation state is like a bookkeeping, but it's very useful bookkeeping because we assume, for everything it's 100% ionic for all compounds, whether it's ionic or covalent. If it's purely covalent, we're going to it's going to be a tie. So for example, if it were, except, when we have two of the same atoms, like an A bonded to an A type bond, like for example, hydrogen-hydrogen bond. A hydrogen-hydrogen bond, we would not consider that ionic, or even a fluorine-fluorine bond. Fluorine, the Lewis structure looks like this, where it has an octet around each fluorine rather than a duet. Okay, so except for when we have like this homogeneous type bond. And so even though this isn't that polar, even though this isn't that polar, 0.8, we're still going to treat it as 100% ionic. When we treat it as 100% ionic, we have winner take all. Winner takes all electrons. Winner takes all bonding electrons. What that means, who's the winner? The winner is going to be the more electronegative species. In this case, the winner will be nitrogen or hydrogen. Which one wants the electrons more? Which one's more electronegative, nitrogen or hydrogen? Nitrogen is more electronegative at a 3.0. And so this means we divide the electrons differently. So how we do this is like this. It's a winner take all. So nitrogen versus hydrogen, who wins these two electrons in the bond? Which one? Sorry. Nitrogen. Winner take all. That means nitrogen takes both those electrons, leaving hydrogen with no electrons. Same thing here. Same thing here. Well, lone pair belongs entirely to nitrogen here. And so nitrogen ends up with 8 electrons. Hydrogen ends up with no electrons. And so if we have nitrogen with 8 electrons, nitrogen normally has 5 valence electrons. And so if it has 5 valence electrons and it ends up with 8, then it has 3 extra electrons. 3 extra electrons would be 3 extra negative charges. And so that means the oxidation state of nitrogen here is -3. -3 because it has 3 extra electrons beyond its normal valence. But hydrogen has 0 electrons, normally has 1 electron, so each hydrogen ends up as a +1. And so even though this compound isn't what we call ionic, when we do oxidation state, we assume all the bonds are 100% ionic, and then we can figure it out. Now, that's not accurate. However, even though it's not accurate, we do the same thing for everything, and this gives us a useful number to dictate, because when we look at ammonia, we'd say, at least chemically, in terms of redox, would ammonia be electron rich or electron poor? Electron poor? Poor? Poor because of the long time ago, the first day of class, I said that chemistry is a mix of theory plus observation. And so what we do is we correlate these theoretical numbers with something we observe. And so that requires a bit of memorization to do that. When I say electron rich or electron poor, you have to have some prior knowledge for something like that. In other words, like water. If we look at water, winner take all. Winner take all, who's going to win the electrons, oxygen or hydrogen? Oxygen. So oxygen ends up with 8 electrons. It normally has 6, so it ends up with 2 extra electrons. Those 2 extra electrons are going to give us 2 negative charges for each oxygen. Hydrogen ends up with no. So is water electron rich or electron poor? Or neither? You might say it's electron poor because of the hydrogens. Well, if it's electron poor because of the hydrogens, that must mean that water must be a pretty good oxidizing agent, because oxidizing agents are electron poor. Is water a good oxidizing agent? No? No is correct. Well, then you might go, well, it's electron rich because of oxygen. Oxygen is -2. That must mean it must be a good reducing agent. That means, good reducing agents, we can build a fire. So if you ever run out of firewood, you could use a bucket of water to burn instead of firewood to burn. Is that going to be very successful? No. And so what we say is that water is pretty stable. That means these are neither electron rich nor electron poor. It's just electron happy as is. It's unreactive. It's stable. Is ammonia as stable as water? No. Ammonia, you can burn this stuff. You don't want to burn it, but you can burn it. It will burn. If it burns, that means it's electron rich. You can burn it. That's why you don't want to mix ammonia with bleach, because ammonia is electron rich, bleach is electron poor. If you mix ammonia, electron rich, and bleach, electron poor, you're going to get a redox reaction, potentially explosive redox reaction. So this is why they say never dump ammonia down the sink with bleach. What has happened in the past is it's gotten very hot and created like a pressure explosion or something. People get a face full of bleach and ammonia. And so those are little reference points that we memorize. You memorize that kind of stuff. And how do you memorize it? Well, I already talked about ammonium. Ammonium and ammonia share the same oxidation state. In fact, I talked about ammonia before as well. I told you it's electron rich. Ammonia and ammonium are both electron rich. And it's electron rich. These are little reference points that you log in and memorize. These are that you can't really. This is why AI, artificial intelligence. There's only so much you can do with artificial intelligence. You need a higher degree of thinking to make these simple relations. It's not some simple algorithmic thing. So this oxidation state. Oxidation states are useful for redox. We compare, when we compare, like for example, if you look at the octet, is it easy to determine it's electron rich? No, because water has an octet too. You look at water, oxygen has an octet and hydrogen has a duet. So water's the same as ammonia. But when you look at oxidation states, then we might be able to get some clues, some additional information. Well, oxidation states is something we already talked about. And there's different ways we do oxidation. We can do oxidation states based on Lewis structure. Doing oxidation state based on Lewis structure, we draw little boxes like this to figure it out. And doing oxidation states based on Lewis structure is quite useful for seeing the different behavior in atoms within a molecule. There's a third way of, this is number 2, oxidation state. There's a third way of counting electrons, which are going to be very useful for Lewis structures. For Lewis structures, we like to count electrons using formal charge. With formal charge, we make the opposite assumption. With formal charge, we assume all bonds are 100% covalent. In other words, we have a 50-50 sharing of bonding electrons. So when we look at ammonia, nitrogen, nitrogen's more electronegative, so it pulls the electron closer to it. And so if we're looking at the electron cloud would be distorted towards nitrogen because it's going to build up more negative charge density, more electron density over here. But what we do when we do formal charge is we ignore that. This is going to be a polar bond. We're going to say it's a non-polar bond. Split it down the middle. Split it down the middle, split it down the middle. It's not really split down the middle. So we're going to share the electrons equally. In reality, they aren't shared equally, but this is a way for counting, electrons. And so if we split them equally, then nitrogen ends up with how many electrons in this? Well, nitrogen ends up with 1, 2, 3, 4, 5. If nitrogen ends up with 5 electrons in the box, how many is it supposed to have? Well, nitrogen's supposed to have 5 electrons. And that means it's broke even. That is, there's 0 formal charge. I'm going to circle formal charges. I'm going to put oxidation states in parentheses. Now, each hydrogen ends up with 1 electron. Now, hydrogen normally has 1 electron. And therefore, it broke even. So each hydrogen has a 0 formal charge. And so everybody broke even. Nitrogen contributed 5 electrons, it got 5 electrons back. Hydrogen contributed 1 electron, it got 1 electron back. So that's what we call formal charge. Okay, did anybody do carbonate? Yeah? Take a look at carbonate. We'll do it from the beginning here. Carbonate, CO3 2 minus. Carbon has 4 valence electrons, 3 oxygens, that's 6 electrons each, and then the -2 charge. A -2 charge means we have 2 extra electrons there. And that's 18, 22, 24 electrons. Is that what you got? 24 electrons. All right. Now let's take a look at the structure. Which atom did you put in the center? You put carbon in the center like this, and then the 3 oxygens like that? No? How did you do it?
Well, I did
Straight line, like carbon like this, and
yeah,
okay, then where did the next oxygen go?
on the
On the
other side.
other side? And where did the last oxygen go?
On top
On top
of carbon.
of carbon like this? Okay, now, we're going to talk about the shapes of these things later, but I treat these as the same, Later on when we talk about the shape, because Lewis structures, we don't have to be accurate. Like for example here, if I look at the angle here, it looks like I have a 90-degree angle, but that's not accurate at all. That's because in Lewis structures, we don't have to be accurate. We just have to show the connectivity. The 3-dimensional structure we're going to show later. And so this is perfectly fine, that's good. And this is fine as well. Doesn't matter, we'll just use yours here, that looks good. Okay, when we look at the shape later on, then we'll make a distinction here. Okay, then what did you do? Okay, before you do the double bond, we need to see if we do have to put a double bond there. And so what we'll do is we're going to complete the octets by using lone pairs like this. If we do that, then everybody has an octet, correct? This is just following the steps. Everybody has an octet, so everybody should be happy. Except there's a problem with this structure. What is the problem with this structure? Yeah, I have to have 24 electrons. Can you count how many electrons I have here? How many electrons do I have in this structure? 26 electrons. 26 electrons, I have 2 electrons too many. So somebody's got to lose. I have 2 electrons too many, so who should I take it from? Should I take the electrons from oxygen or carbon? Carbon. Why carbon? Well, carbon wants 8, like it wants an octet to fill its second shell. There's another reason why carbon. Has to do with if you're in a tug of war, you know, you got to take them. Carbon doesn't want to let them go. If you got to take them, then which one's easier to take electrons off of, carbon or oxygen, and why? Yeah, oxygen is more electronegative, meaning it's going to be more difficult to take the electrons. Carbon's less electronegative, so carbon's not going to put up as much of a fight. Therefore, it's easier to just take them from carbon than it is from oxygen. Why? Well, let's take a look at the electronegativities there. Oxygen is ranked at the 3.4. You know, it's second only to fluorine. Fluorine's at top, so oxygen's number 2 in terms of electronegativity. Carbon's at 2.6. So oxygen is significantly more electronegative than carbon. Electronegativity, how would you define electronegativity? Give me a quick definition of electronegativity.
Just the polarity of the bond.
Well, you know, we use electronegativity to determine the polarity of a bond, but electronegativity is not defined as the polarity of a bond. Electronegativity is defined differently. We could use, we'll just see what the book says. The ability of an atom of that element in a molecule to attract bonding electron pairs to itself. I don't really like this definition. It doesn't have to be bonding electrons. It doesn't have to be in a molecule. You know, that's why when I used to study for classes, I would look up. You know, this is pre-Wikipedia, pre when everything was on the web. What I would do is I'd go into the bookstore and look up different books, you know, look at in different books and library, and then see, you know, how did different books define it. You know, that gave me a better, broader understanding of things, for sure. So I like to look at many different sources. Here's a definition. Electronegativity is a measure of the tendency of an atom to attract a bonding pair of electrons. It's a tendency for, it's not just a bonding pair, it's for electrons in general, whether bonding or lone pair, it doesn't matter. So I don't like that definition either. But, you know, I'd look at a lot of definitions and then see, you know, to get a better idea. Electronegativity is a chemical property that describes the tendency of an atom to attract a shared pair of electrons or electron density towards itself. It's also ability to attract its lone pair. You can pull them in tighter. And also ability to attract electrons off adjacent atoms. And so electronegativity, they should give it a more general definition, and that's just the ability to attract electron density, electron cloud. See what the Chem guide says. It says the same. Shared electrons. It doesn't have to be shared. Anyway, theoretically it was defined, and
the numbers come from, you know, the ability to track shared pair of electrons, so I can understand why they did that. But we use it in a broader context. That is, yes. So. Just the ability to attract electrons. It's
All right, so that's what we did here. We add unshared pairs to complete the octet around all atoms except hydrogen. We did that. However, when we calculate the number of valence electrons in the tentative diagram, 26 electrons, and compare with the actual 24 electrons, then there's a problem. We have too many electrons. If the diagram has more, remove lone pair from central atom and terminal atoms and replace, well, this is not exactly correct. We just removed it. This is 2 steps in one. So we removed it from here. Now, the second part of this is, now what we've done is carbon. Carbon doesn't have an octet. Carbon only has 2, 4, 6 electrons. And so it's not going to completely fill that shell. How many more electrons does it need to fill the shell? 2 more. So if we remove a pair of electrons from here, then we have a problem. We don't have an octet anymore. And so what they're saying in the next step, and I would have broken this down into 2 steps, is to take a pair of atoms from here, electrons, a pair of electrons from here and make a double bond. But does it matter which oxygen I pick from? I have 3 oxygens. It doesn't matter. They're all going to be kind of the same. In fact, I have something here that I have to deal with. That is, if I pick it from the one on the right, I get this structure. If I pick it from the one on the top, I would end up with this structure. So let's take this one, bring it down in here. Leave this one. Oops. Leave this one as is. These 2 structures are equivalent. The only difference is where I took the electrons. And then you might think, well, if that's the case, then they're exactly the same, or maybe they're the same, maybe they're different. It actually is the same in one sense and different in another sense. They're the same because it's the same structure, 2 single bonds to an oxygen, 2 single bonds to an oxygen, and a double bond. The difference is in which oxygen. Now, we have to define the oxygen. That is, we have to prevent this molecule or ion from moving, and then we generate like that. We could have picked the one on the left. If we picked the one on the left, we would have had this structure generated. And so we could have picked it from any of the 3 oxygens. And in fact, we do to get these. These are called resonance forms. There are going to be 3 resonance forms because we have 3 choices of oxygen to pick from. Now, when we do Lewis structures, we do one more thing. We determine the formal charge. So are there any formal charges here? So what was the, for formal charge, what do we do? We assume that the bonding is 100% ionic or 100% covalent for formal charge. We assume the bond is 100% covalent. And then if it's 100% covalent, then we do a 50-50 split of the electron. And so if this were, well, let's count the electrons. This oxygen, we don't have to share these because these are lone pairs. They belong entirely to this oxygen. And so these are not going to be shared with carbon. And so this oxygen has 2, 4, 6 electrons that belong solely to it. And then we have these 2 electrons which are shared. Now how should we split that? Half and half. So that's 2, 4, 6, and then it's going to get 1 of the 2. So that means that this oxygen has 7 electrons. If this oxygen has 7 electrons, How many electrons is oxygen supposed to have? How many valence electrons is it supposed to have? 6. So if it has 7 electrons, it came out with 1 extra electron. If it has 1 extra electron, does that mean it's plus 1 or minus 1? 1 extra electron, plus 1 or minus 1? Minus 1. And so formal charge we circle. So this one's going to be minus. Let's take a look at this oxygen over here. If we look at this oxygen, there's 2, 4 that belong to it. Now each line represents 2 electrons. So there's 2 in a double bond, we'll have a total of 4 electrons. That total of 4 electrons is going to be split down the middle. So 2 of the electrons go to carbon, the other 2 go to oxygen. So this is 2, 4, 5, 6. How many electrons is oxygen supposed to have? Valence electrons. It's supposed to have 6, and it ends up with 6, so it's even. Therefore, it's got a 0 formal charge. Now, how about this carbon? This carbon, we're going to do a 50-50 split. So from this bond, it's going to get how many electrons? 1. From this bond, it'll get, and from this, 2. So 1, 1, 2 is 4. Carbon ends up with 4 electrons in this structure. How many did it contribute? Carbon contributed 4. So it contributed 4, it got 4, it broke even. If it breaks even, then we call it 0 formal charge. It neither gained nor lost electrons. It came out 0. How about this oxygen here? Tell me what it is. Yeah, this one's going to come out negative. That's a negative formal charge because 2, 4, 6, 7, it came out ahead. Now what we do is we're going to sum up all the formal charges. So it's going to be negative 1 is negative 2 plus 0 plus 0. So the whole thing is going to be what charge? The whole thing is going to be a negative 2 charge. So what we're going to do is we're going to sum up everything in the circles here and then write that as the net charge. This is the net charge. And so carbonate has a net charge of minus 2. Each of these oxygens has a minus 1 charge on it. Now usually the 0 formal charges we don't show. And so let's take a look at what happened to the formal charge here. Do you see that? Can you tell me which of these oxygens is negative? This one, 0 or negative?
Negative.
Negative. This one,
0.
carbon?
0.
This oxygen, negative. And so this one is going to have a net charge of minus 2. So when we do the brackets, we're going to sum up all the formal charges to get the net charge. And the same thing over here. You can see this top one is going to be negative. This one on the bottom right is going to be negative. And the whole thing is going to be negative 2.
That all of that is the same, right?
Yeah. All these structures are the same. They're the same, but the thing is it's where the electron came from. Which oxygen sacrificed the electron, contribute to the structure. And we have 3 choices of oxygens that can sacrifice it. Bicarbonate's a tough one. Bicarbonate, even Chem 1A students get bicarbonate wrong sometimes. So bicarbonate, that's why I started with carbonate. Carbonate is a little less tricky. But that would be carbonate. We call these resonance forms. Double-headed arrow, the 3 resonance forms of carbonate. This shows that these resonance, the double-headed arrow is used for resonance. Resonance form. So when we draw up the Lewis structure, we draw out all three resonance forms like this, and then put the formal charges, and then the net charge on it. Let's take a look at bicarbonate next. Look at bicarbonate. Hydrogen contributes 1 electron. Carbon contributes 4 electrons. 3 oxygens is 3 times 6. It's 18 electrons. And then the charge. The charge is -1, so that's 1 extra electron. So we'll just add it up. 24 electrons. Okay, 24 electrons total again. Now, tell me what the structure looks like. So we'll put carbon here. What do you have attached to the carbon? Oxygens. So we'll do 3 oxygens. Yeah. Now, where did you put the hydrogen? Next to the oxygen on the right. Well, let me show you the most common mistake for bicarbonate. The most common mistake is this. They put the hydrogen on the carbon. Hydrogen on the carbon. When we have an acid anion, like this, the acid anion, the acidic hydrogen goes on the most electronegative element. And so this would be considered non-acidic hydrogen because it's going on carbon. The carbon-hydrogen bond is very nonpolar. It's like methane. If I think about methane, think methane here. If I think about methane, methane looks like this. Is methane a good acid? No, methane is not a good acid, and it's because these are non-acidic hydrogens. Non-acidic hydrogens. It's because, the reason is because of the bond polarity. In order to be an acidic hydrogen, the bond has to be polar. The carbon-hydrogen bond is not very polar. In fact, we call it non-polar. And so if we look at acetic acid, this would be the Lewis structure for acetic acid. If we look at acetic acid, then the acetic acid has 4 hydrogens, but 3 of them are bonded to carbon. 1 of them is bonded to oxygen. The acetic acid is considered monoprotic. These 3 hydrogens are non-acidic because the carbon-hydrogen bond is pretty nonpolar. Whereas the oxygen-hydrogen bond is quite polar, so this hydrogen is acidic. The more polar that bond is, the more positive the hydrogen is, because oxygen is going to try to take the electron away from hydrogen, making it more and more positive. Versus here, it's more of a tie. I mean, they aren't exactly equal. I mean, when we look at the electronegativities, hydrogen's at a 2.2, carbon's at a 2.6. So there's still, carbon's still stronger by about 0.4. But 0.4 difference in electronegativity is not that significant. In fact, it's insignificant. And so therefore, the carbon-hydrogen bond is considered nonpolar. Nonpolar means it's kind of a tie. If they got in a tug-of-war for the electron cloud, it's kind of a tie. Carbon just wins by a slight margin. Versus an oxygen-hydrogen bond, oxygen is at 3.4, hydrogen is at 2.2, giving us a 1.2 electronegativity difference. A 1.2 electronegativity difference, although not ionic, is quite polar. This is a polar covalent bond, making this hydrogen much more acidic. And so it has to do with the electron cloud. When we look at the electron cloud and the carbon-hydrogen bond, it's close to a tie. Therefore, it's going to look pretty symmetric. This carbon is a slight winner here. But when we look at this bond is very asymmetric in the electron cloud. That is, oxygen is much stronger. And what that means is that this hydrogen is much more positive than this hydrogen here. there's a lot less electron cloud next to it. It's closer to +1. The other thing is, there's another problem with this, because if I left that, let's say I forgot that acidic hydrogens go on the most electronegative element. What would the next step be in this? Let's take a look. The next step would be to add unshared pairs to complete the octets around all atoms except hydrogen. So let's do that. So I did that here. So carbon has an octet and all the oxygens have an octet. So it looks good. Calculate the number of valence electrons in the Lewis structure. So let's figure out how many valence electrons do I have. Well, how many electrons do I have in this Lewis structure? I've got .26 electrons. So I got the same problem. 26 electrons is too many electrons because I only have 24, so I have to remove it. And so who am I going to take the electrons from? I have to take it from oxygen. I have no choice. Which oxygen? Does it matter? No, it doesn't matter. So let's take it from this oxygen. I'll take a pair from this oxygen, which means that oxygen no longer has a octet. How did I fix that over there? I took a pair from oxygen, or carbon. I took a pair from carbon, and then I formed a double bond. And so let's take a pair here and make a double bond. Is that going to resolve my octet problem? And so I'm going to take one pair from here and make a double bond. Did that fix my octet problem? No, I still don't have an octet on this. And moreover, take a look at what happened to carbon. Carbon I have 2, 4, 6, 8, 10. So it only takes 8 to fill that second shell, so that means the extra 2 electrons have to go into the next shell. Is that going to be favorable to go into the next shell? No. So I don't want to have more than an octet around carbon because it would go into the third shell. 2 electrons in the third shell is going to be that stable. So how am I going to do this? How can I make an octet? Somebody help me here. How can I make an octet around that right oxygen? Yeah, I can't. I can't make this structure work.
You can add to the carbon.
I can add 2 to the carbon. So if let's say I take 2 off here and then put 2 here. No, that gives me 2, 4, 6, 8, 10. 10 electrons is not going to happen. I fill the shell, I don't want to go above it. So there's no way to make this structure work. So we've got to try a different structure. The different structure is going to look like this. You're exactly what you're saying. So you put the hydrogen here. Is that right?
Yeah.
Yeah. Well, it doesn't matter. We can put it here, here, or here. But this looks good. And then we complete the octets. We complete them first to the oxygen because oxygen is more what? gonna complete the octet to the oxygen versus the carbon because oxygen is more electronegative. Okay, and then we're gonna complete it to carbon. Like that. Okay, then we're gonna continue this and